3, 2, 1, live!
Welcome to Chemistry in the AM. This is M introducing Mr. Silvius. Take it away.
Thank you. I am Mr. Peter W. Silvius, not to be confused with Michael. Quick review of what we saw the other day, electrochemical cells. This is a simplified battery with 2 beakers and so on. Metal strips, electrons going from the anode to the cathode, because the cathode is positive. Same root as anion, cation. Cathode is positive, anion is negative. We have a memory aid, red cat. Reduction happens at the cathode. And with your oil rig, oxidation is losing electrons, reduction is gaining electrons. And red cat working together, you can figure out which metal is which. We went over some terminology. Then we had some simple calculations. And I mentioned then that when you try these and you multiply an equation by 2 or 3 or whatever to balance electrons, you do not multiply the voltage. The only thing you can do with the voltage is flip signs. Now, we took this one up as a group yesterday, didn't we? 3A? So, the other one, H2 plus Cl2 and the I negative in the permanganate. Okay. That we did already. Well, B, I have it up here. And I'll put up C as well. Let's see here. H2 plus the 2H. That's the half reaction. And it has a 0. Cl2, Cl negative. By the way, this is a redox reaction set up without a metal. It still has electricity. More about that, but you could use that with an inert electrode. Use something, carbon or platinum or something like that. Anyways. And I just put it on the side. It wasn't asked for, but reduction at the cathode, oxidation at the anode. Just getting used to identifying which one is the anode and which one's the cathode's reaction. Okay? So 1.36 volts is only one of the 3 marks I'd be giving, right? I need that. We need the reaction set up and the final thing. And you need to be able to, because I'll be asking which one's the anode's reaction, which one's the cathode's reaction. So I'm just showing you. You typically, I give a question like this, but I ask for a little more, and I want 3 things. Knowing which one's the oxidation anode, reduction cathode, overall reaction, which is quite simple in these cases, and the voltage. With units, right? So C. C was a little more because it actually had hydrogen and oxygen involved with that half reaction, the MnO4 one. But hopefully you got it. And you got decimal 99 for the volts, the overall reaction. Now, I didn't ask you for anode and cathode, but red cat reductions at the cathode. You can quickly tell it's reduction because reduction is gaining electrons. The electrons are on the left side. So that's where we left off. The calculation part of it is actually quite simple. Like the adding the volts or subtracting. So relies mostly on what we've known before about redox balancing reaction. So a little more to work on with this. I'm going to do it. I'm just waiting though because I can see some people are making corrections as necessary. And let's try this out. Or no, not quite. I guess I could pause while I'm waiting. Back to this. For this cell, only work on the black stuff. We're not going to do 2 yet, okay? So for this cell, jot this down and we're going to sketch and label this, but I want you to have this down first, okay? I'll pause the video while you copy that down. Okay, so we're going to work through this. So if I give you this information, how do you come up with the diagram? Now, I'm not marking you on your art, but it should be somewhat reasonable. How do you draw it? Oh, sketch and label. So I'm going to go back and forth. So, the first thing you should do is to draw. I don't care if you make your beakers look like this, or if you make your beakers look round, like top and bottom. That's not the issue, is what I'm trying to get at. So, I being really awesome at this stuff. There's my two beakers, okay? So, you're going to draw two beakers. You know what this generally is. I'm going to draw salt bridge tubing. I'll automatically put KNO3 on the salt bridge. Unless stated otherwise, that's my default salt bridge. I recommend it. Okay. I'll put in a liquid level. Not that there's waves in a beaker, but it just kind of makes your head think, okay, that's what. And then I typically put the anode on the left, negative to positive. You can do it the other way around. Doesn't matter. So if this is the minus side, this one has to be the positive side. And you can do this in mirror image. It doesn't matter. But sketch and label the anode and cathode. Once I have one side declared negative, what is the negative, the anode or the cathode? The anode. So I go with A, label the anode. B, the cathode. Now, I'm labeling as much as I can that isn't particular to this. Now, the direction of electron flow. The direction of electron flow, well, I could put a strip here, an anode there, and a strip here, that's a cathode. And it connected. I don't care if you put it as a light bulb or a meter or something that's showing there's electricity flowing. Anode to cathode, electrons are negative. So which way do they flow? From positive to negative or negative to positive? Right, they're attracted. So I will put E negatives. I'll put it on this side. Okay? Does that make sense? You have to label the diagram. I don't think you drew it. Oh yeah, you did on the first page. Yeah. You did. That's right. You did. Okay. Everything else now is actually particular to this system. So we've got to figure some things out. Which side is, what are these ones are cadmium and which one's silver? Well, we've got to break this down. So far, this is generic. This is the start for any diet. Now, this is a notation that tells me, without the full reaction, that you start with cadmium and you go to cadmium 2+. You start with silver ion and you go to silver. So I'm going to put those down as my passive. So, boom, boom. We start with cadmium. Go to cadmium 2+. Big space on the right for my electromotive force in volts. My silver ion goes to the element. I'm going to put in my electrons right away. This is pretty easy. 2 electrons, 1 electron. And now I'm going to look up my volts. Let's just do this all at once. So when I look up, I'm doing this before I do the multiplication, because I'm reminding myself multiplication doesn't do anything. changes the sign. So, so the cadmium one, I'm scanning, I don't know it off the top of my head. What is it? Now it's not, but you guys don't. So hold on. Sure. It's -0.4 as listed though, but you notice that it's backwards? So always take a look. Like it's backwards for what we have written. So it's reversed, so we reverse the sign of positive. 0.40. So one will always be reversed from the chart because they're all listed as reduction. You could put flat. I'm emphasizing the positive. They're always so lectin. 0.8. It is 0.80. You're really good at looking those things up on a chart. That adds up to 1.2. Total. Pause. 1.2. Full. Okay. Now, I haven't finished this. I've only got one of the 3 marks of it. You have to still balance for electrons. But by the way, before I move on, we're getting positive batteries. That means that's a battery system that will give away energy. So it's electrochemical stuff. Sometimes, if you add something up and it comes out negative, well, that's a cell system. For that reaction to occur, it requires energy. You have to feed it in. Why on earth would you need something that takes in energy? Well, not for battery reasons. But there could be, remember how something gets deposited on one of the strips? So if you wanted to electroplate gold or silver onto another metal, you would probably do it that way, right? And you'd use energy to do it. Possible. Or every night you want to recharge a battery. You're feeding it energy, and you're just running the reaction system in reverse, right? Electrochemical. So there's an example of negative voltage. So all negative voltages means it doesn't happen spontaneously on its own. It requires energy input. Positive means this will give off energy and it'll happen spontaneously without energy. Okay? Those are so back to the easy part now that we've done really tough. Balancing this, because there's no oxygen or hydrogen, we just skip to the electron step and we say, well, we need 2 electrons here, so we're going to get 2 silvers of the ion and the when I add it up, I've got the electrons canceled at design. Cadmium plus 2 Ag plus cadmium ion, 2 silver only. Now, this means that it's not only balanced for atoms, because I bet you without the electrons involved, it wouldn't occur to you to balance for charge as well. But there's a total of 2 positives on that side, 2 positives on this. So it's balanced for charge and for atoms. Okay. So, questions D and E, we did F, the total voltage. But what's the oxidation half reaction? What's the reduction half reaction? Okay, good. Back to this. Red, blue. Oxidation is losing electrons. Red, blue, red, right? Reduction is gaining. Oxidation is losing electrons. That's the cadmium, throwing them out, right? I'll just put points. And then reduction is gaining electrons. That's where they're added in. Now, I didn't ask for this directly here, but we're going to label the diagram. Oxidation happens at the anode. Reduction happens at the cathode. Okay. But now I know Go back to my diagram. See, the anode is the cadmium. So the solid, the element cadmium, that's what this strip is. CD, cadmium is the metal. The metal involved here is Ag, cathode, reduction of cathode. Then that means the ion in solution, this one here, Ag plus. That's not the metal, that's in solution. Cadmium is in solution. Now, you're not going to just have elements. It could be nitrate or sulfide or sulfate or something like this. It'd be like silver sulfate, cadmium, stuff like that. It'll be matched with a negative and yeah. How do I know what's in the bead? So first of all, we know the red cap, right? So I knew that silver is the metal strip. Okay, that makes sense. So if this is the solid, because the elements are solid, right? The solid. So the other thing, the ion will always be in solution. The ion cadmium is without the charge, the elements without the charge is the solid cadmium ion. Matched with another anion, but it's a spectator ion, so it's simplifiers. So that's the kind of thing we're going to have to look at. Let's just see here. I think I might have this one scrolled out. We won't do the other diagram when I code it. Not this one here. That's just what we worked on. Well, let's just see here. Find the voltage of a cell with silver and chromium metals. I didn't even tell you what the ending is. But you'll have to look it up. Well, chromium on your sheet, you might as well just use your iron or your electrode sheet. Chromium can turn into a fine one on there. And silver. And you're going to have to make, and here's my challenge, of a cell, and I didn't say whether it's positive or negative, but let's assume that it comes out to be positive. So you're going to mix and match only one set of, when you flip something, it becomes negative or positive, switch sides. You're going to have it in the way that it adds up to a positive voltage. That's your challenge right now. I'll give you a few minutes. So taking this up, I told you your challenge was to find it so that it's a positive voltage. So I look up the two metals. I see that at positive 0.80 volts, you've got silver plus an electron goes to silver ion plus an electron makes silver salt. Lower down, chromium 3 plus, 3 electrons chromium, negative 0.74. So I know I have to flip one of them, and I want it to add up to be positive. Which one do I flip? Positive or the negative? The negative, right? So I'm going to list the silver as is, because it's already positive. That's Ag plus an electron. And when I'm gaining electrons, reduction is gaining electrons, so it'll rip, right? So, reduction is gaining electrons, I put it down. Ag plus electron. Ag solid. And make sure that I write the motor force. Adding because it's ending up in the product. The electrons are absorbed into the zinc, or the chromium one. It's flippy. So I'm going to write it exactly backwards. So I'm taking care of this. Cr 3 plus and voltage in this case, potential drop is flip sign 0.74. go. Now the math, the arithmetic isn't too tough. I just add them up. I have 7 and 8 is 150, so 150. Okay. But I still need to do the half reactions. Balance them up. So I'm going to do this, or I do it on a match electrons. It's the silver reaction, the reduction reaction. Happens to be cathode. Yeah. Exactly. Of course, everybody's smart and good. Honestly, you're there we are. This is in the textbook. You are going to flip to and read page 673 through 82. What types of batteries? Okay? We will discuss and formulate some notes afterwards. But I need you guys to read this, so you might want to jot down a brief list as you read. Okay? Types of batteries, big jot notes. And I'm going to go scan these pages and put them on the you don't have to be really detailed. Yeah, you got a lot of time too. You got 20 minutes. Okay. I have put them online too, so if you don't get done, go ahead. Sorry.